effect of a toy characteristic must vary randomly over people. So it goes on the people line, child ID. Otherwise, adding random effects proceeds just like the usual. Other questions? All right, well, it's only Monday, so let me know if anything comes up. Off-topic announcement. This morning I sent out an email to all of your department chairs advertising my fall course, Latent Trait Measurement and Structural Equation Models. It's coming back in the fall. Several of you took that last time around. It is cross-listed as EPSI 906. So some of you may have taken that version last fall with Jonathan and using R. My version will use M+, but it will be the same content. So spread the word if anybody would like to come. Auditors are always welcome as well, space permitting. So, any other questions, logistical things, anything else? Anything you want to talk about before we dive back in? Anybody come up with what flavor this is, if not lemon lime? Green. Green? It's green flavor. I will accept that, because one of my other favorite flavors to drink is blue. Blue drink, such as blue Gatorade, blue juice. Blue is good. Blue Kool-Aid? Blue Kool-Aid is awesome. If you put Splenda in it, then it doesn't have 1,000,000 calories, and it's even better. But hardcore blue Kool-Aid, excellent. All right, I'll take it. It's green. It's green drink. That's fine. Like green tea, except it's green soda. Or pop, if you grew up in the Midwest. Anyone say that? Oh, that's right. Everything is a Coke, right? As a generic noun. Yeah, I've heard that one too. It's a green Coke, as it were. So what have we been talking about other than green drinks? Clustered data. Give me a synonym for clustered data. Nested. When do you know that you have clustered data? People in groups. Two options for modeling group differences, right? Group is a fixed effect or group is a random effect. Group as a fixed effect is appropriate when you don't have very many groups and you want to know about their specific differences. Groups as a random effect, more appropriate if you want to predict why they differ from each other. How does what you've learned so far apply? Tell me about multi-level models for clustered data. Anything you remember. It's a deliberately broad question. Are we still making piles of variance? Yes? Are the piles still starting with between or within? Yeah? What's the suffix? The second half of the word. It used to be between and within person. Between and within group or cluster. You can cluster and group are synonyms to me. And let's see. What does an intraclass correlation represent in clustered data? Proportion of variance between groups, that's one way to say it, or equivalently, if you use the word correlation in the sentence instead, intraclass correlation is the expected correlation of people from the same group. Yep. So if the intraclass correlation is really high, the people are a lot alike, which means there's very little within group variation, but a whole lot of between group variation. If the intraclass correlation is low, people are very different from each other, meaning it's mostly within group variation and not as much between. Is there any cutoff of intraclass correlation below which I can say, nah, it's fine, just use regression? Nope. What about a significance test? What if I have a non-significant interclass correlation? Then is it okay to go back to regression? Yeah, if I put predictors in level 1. Whenever you have a level 1 predictor, it will explain residual variance. That will make the random intercept variance go back up and your interclass correlation go back up. So only if at no point in the analysis do you have a random intercept variance that's above 0, that's when you can go back to single level models. But just because you start that way doesn't mean you'll finish that way. What's a design effect? And you answered this last time. And you gave a good answer, but I'm going to make someone else answer. What's a design effect? It is an adjustment to the sample size that you need, yes. So it's total sample size divided by design effect. Gives you your effective sample size. Design effect is 1 plus the number of lower level units minus 1 times the interclass correlation. So to the extent that you have a lot of people per group, or you have a large interclass correlation, your design effect is large, meaning you don't really have the level 1 sample size you think you do. So it's something that's useful for descriptive purposes. It's useful in planning studies to calculate power analyses. So in terms of power for level 1 predictors and level 2 predictors, in the context of cluster data, what's level 1? People or group? People. So you would think your power to detect people things depends on the number of people, but that's actually your best case scenario. Likewise, the power to detect group level predictors at level 2 depends on the number of groups. Your effective sample size in terms of your number of people depends on the number of people per group and their interclass correlation. It's going to be somewhere between the total number of people as your best case scenario and the total number of groups instead as your worst case scenario. Interclass correlation would correspond to effective sample size being your total number of people for real. Interclass correlation of 1 would correspond to being the number of groups instead. So what if I'm going to recruit, let's say, 10 schools. I'm going to assign 5 schools to a control group and 5 schools to a treatment group, and I'm going to sample everybody in the entire school. Let's say that I'm doing this in DC, or someplace big, right? Let's say I've got 30,000 students. Do I have lots and lots of power to detect treatment versus control differences? Heather, you're shaking your head. Why are you shaking your head? Because you're right. It matters how many groups I have. From the perspective of trying to figure out why some schools do better than other schools, I've got 5 and 5. Even if there are 30,000 people in those schools, I've got 5 and 5. So power is always level specific. If I were interested in predicting level 1 effects, so why do some people do better than others, I have somewhere between 30,000 and 10, depending on the interclass correlation and the number of people per school. So that's what design effect does. It reduces your sample size into effective sample size as a function of the interclass correlation and the number of people. Let's see. So which kind of predictors then in cluster data can have random slopes? People things or group things? People things, level 1, more broadly, over level 2. So we did an example using real data. We'll walk back through. Predicting math amongst about 13,000 kids and about 200 schools, I think, 94 schools, excuse me. This is a cross-sectional example. So math had an inter-class correlation from an empty model of 0.15. 15% of the variability in math had to do with which school you go to. 15% was due to school mean differences in math. 15% was due to the school random intercept. You can say it all of those ways. So I have a significance test here for whether or not there is significant school dependency. That's another way to say it. Correlation and dependency are the same thing. I have a significance test comparing this two-level model to a single-level E-only model, and that significance test says, yes, this model fits better. The effect size for that piece of information, then, is the intra-class correlation. So, yes, there is significant school dependency. How significant is it? P less than 0.001. How big is it? 15%. That creates a design effect of 42 in this example. We then added a student-level predictor at level 1, free and reduced lunch, where 0 is people who pay for lunch and 1 is that they get a discount of some kind. And we saw that that effect was statistically significant and fairly large, 9-point difference between students who do and do not pay for lunch. That fixed effect at level 1 reduced the level 1 residual variance by 5%. So of the 85% of the variance in math that had to do with within school differences, 5% of that is accounted for by student free lunch. But at the same time, of the 15% of the variance in math that was due to school mean differences, 40% of that was captured by student free and reduced lunch. How can that be? How can a student thing account for school level variation? Smushed, yes. And if you're not talking to me, how do you describe a smushed effect? Give me some synonyms. Conflated, that's a good one. Composite, convergence. Broadly construed, it's the idea that you've put in one predictor to try and do the work of two. Student free and reduced lunch is both a student level variable and a school level variable, and you are assuming that the effects are the same across levels when you put in only one predictor. So we fixed it by adding in the level 2 version, which is the mean across students, works out to be the proportion of students in a school that get free lunch. We centered it at 0.3. If I had had access to other sources of information about school level variation, that would be a better source than just averaging over my students, but this is what I had. So then we see that in addition to this -9 effect that we get for a student, we pick up another -16, and that is the contextual effect. It is a level 2 effect that talks about the added contribution of the school above and beyond the contribution of the student. So in this example, if you're a student who pays for lunch, you do 9 points better than somebody else at your school who doesn't pay for lunch. Either one of you, though, for every, let's go 10% more poor kids, because this is scaled from 0 to 1 as a unit, so let's move the decimal over one place to the left. For every 10% more poor kids at your school, everybody's school math score, everybody at your school, their math goes down by 1.6 points. So the contextual effect is above and beyond the individual effect. What is the extra effect of the group and the group's characteristics? If you want to know just what is the effect of the group, not controlling for the individual, that's the pure level 2 between effect, and that's what you get when you add the two together. So at the school level, for every 10% more poor kids, the whole school's mean goes down 2.6. After that, If you're a student who pays for lunch, you do 9 points better. And by adding in this extra level 2 effect to bring the total level 2 effect up to the 26 it was supposed to be, we have then explained another 50% of the random intercept variance for a total reduction relative to the empty model of 70%. So this idea of level 1 plus contextual is what you get when you leave your level 1 predictor either uncentered or centered at a constant. The level 1 predictor in this case has both level 2 and level 1 variation in it. Now, what could I have done instead to make this a little more straightforward? What did we do for longitudinal data that I liked better? Other kind of centering that's not at a number, it's at a person mean centering. In this case, group mean centering, it's at a variable. So we could have taken each student's free and reduced lunch variable value and subtracted off their school mean. That would have created a level 1 predictor that has only within school variation, and we would have gotten the -9 and the -26 straight out of that model. Now, why didn't I do that? Because it's a 0-1 variable. And I didn't want to end up with level 1 values that made no sense because of the way I centered it. So this was an interpretation decision that I made to fit the original free and reduced lunch predictor at level 1, and thus estimate a level 1 within effect and a level 2 contextual effect. We then asked if the level 1 effect varied randomly over level 2 units. In this context, does the effect of student free lunch differ across schools? That's our usual model comparison with 2 degrees of freedom. -2 log likelihood change of 87, so yep. I then used the mean free and reduced lunch estimate here as the middle of a confidence interval of -8. The variability around it is given by the random slope variance for free and reduced lunch, which is 12, and computed a random slope confidence interval, which goes from -15 to -1. So on average, the gap between the haves and the have-nots is 8 points. But across schools, that could be anywhere from -15 to -1. Some schools have a bigger gap. What kind of predictors could explain why some schools have a bigger gap? People things or school things? What do you think? What type of information could explain why some schools have a bigger gap? School things or people things? Not a trick. School things, yeah. So this is where school characteristics would go in, and unfortunately I only have one to work with, but it makes for a good example because it gives us our first instance of intra-variable interaction terms. So we were looking at this model before we left off, model 5. I have added a cross-level interaction, this gamma 1,1 right here. That is the interaction between student free lunch and school free lunch. So the 2 parts of the variable are now interacting with themselves. And we went through this last time. I'll do it real quick again. Each of these main effects of the lunch variables here are now their simple main effects, conditional on when the interacting variable is 0. So that means the free and reduced lunch student variable is specifically for kids who go to a school with 30% free lunch kids. Kids in that kind of school have a gap of -8. This effect of school-level free lunch is specific to kids who pay for lunch. That's when free lunch is 0. And it's 1.9 points for every 10% more poor kids. And the interaction term, based on the pattern of sign here, does the same thing to both of these simple effects. It makes them both less negative, weaker, closer to 0, smaller. So in the case of free lunch, the -8 becomes smaller by 0.4 for every 10% more poor kids, moving the decimal over again. Going the other way, the -19 becomes smaller by 4 for kids who do get free lunch. So the school effect is less pronounced on kids who get free lunch than kids who don't, although not significant. And in looking at effect size, this cross-level interaction, the rule is the cross-level interaction explains the random slope variance for the level 1 predictor if present, or residual variance otherwise. So if present is this case, free and reduced lunch at the student level has a random slope, therefore school poverty level should be one of the reasons why the gap between the haves and the have-nots differs by school. So this is my significance test. It has the power of 94 schools. Cross-level interactions are powered at the higher level. It's not significant, but its effect size in terms of pseudo R-square is, for the random slope here, it's 7%. So 7% of the reasons why some schools have a bigger gap than others has to do with the composition of the school with respect to free lunch. And that 7% is not different than 0. And that's where we left off, right? Katie. Mm-hmm. Yeah, so I don't have to do that, but I'm doing that for the sake of it making more sense. So this -8 refers to a variable that's a dummy code. It's the difference between 0s and 1s. The same is true for the school mean free lunch. The scale of this is a proportion of kids who have free lunch, and it goes from 0 to 1. So that's what a unit means in this case. So like the difference between schools who have no poor kids and the difference between schools with 100% poor kids is 19 points. But to phrase that in terms of every 10% more poor kids, which makes more sense, I move the decimal over and talk about a 1.9 per 10% difference. Yep. Yeah, that variable ranged from 0 to 80% across schools, so there weren't even any schools that had 100% to refer to. So, Andrew? I doubt it.
I find myself having to do it like 4 or 5 times reading the pseudo R-square right now to figure out which variable goes with which one. It's like that really, it's like a very simply for me. Is there a more helpful way to
Yes and no. So it's not just you, number one. Make him feel better. Who else has asked me this question? Yes, I say, not just you. You mean that UN22 is not an intuitive label? You're shitting me. No, this is part of SAS's job security program, right, that it labels things this way so that not everybody can read it without lots and lots of practice. So this name right here is whatever name you gave it, so that's how you can sort of tell the models apart. You can name, I think it goes up to 32 characters in a name of a data set, so you can make that as descriptive as you'd like. This residual will always be called that unless you have a variable on your repeated line, in which case it uses that, like month or something instead. These ones go in order that you listed them in your random statement. So UN11 will be intercept if that's what you wrote first. Intercept is not a default. It's something you have to type. 22 is whatever is next. On the random line, you can also ask for the G matrix to be printed, and then that actually lines up what it prints you the matrix itself. You can say what row and what column. Like 1, 1 refers to the G matrix, row 1, column 1, and then row 2, column 2 is the next diagonal element. It will put the words next to them. So that can help if you can just either remember to ask for that or just remember the order here. But otherwise, if you are inconsistent in how you type, right, like if you decide to stick it first, then you've just messed yourself up because it's going to print it in the wrong order. So I've gotten in the habit of always adding things to the end of my lines. And some of you stick them in the beginning. I've seen that. Just whatever method you use to keep yourself straight, do it the same way all the time. And yes, that's what this refers to. This is the G matrix is unstructured. The first row, the first column, where subject is school ID, meaning it's identifying which section of the G matrix, because we can have random statements with more than one, right? We can have toys and people and all that kind of stuff. So, yes, it's a good question. Another thing that I have here, this NCO4, I am not a good programmer, as you may have noticed with all the homework things. I'm asking you to tell it how many covariance parameters are in your model. That 4 refers to the number of rows here, because then my syntax will know how many covariances to skip when it prints that last table. So your pseudo R-square tables from this macro should always look like this. They should have a parallel structure of what's in model 1, what's in the second model, and the pseudo R-square value should only be printed for the entries that go with the second model. If it doesn't have this structure, then you've not executed the macro correctly. Something went awry. Okay, does that help? Excellent. Other things that I can clarify. All right, so this is where we left off. Do you remember what I told you about this interaction term? Do I believe it? Do I write it up and turn it in? Or have I committed a cardinal sin? I have, right? This interaction term is smushed. Just like main effects, you can smush interaction terms. So whenever you have a level 1 predictor and you want to test whether something moderates it, if you moderate only that level 1 predictor, then you are saying the moderation is the same between schools as within schools. In other words, in this example, I'm saying that that 4 applies equally to the within school effect as it does the between school effect. That's a testable hypothesis. The fix to it may make your heads blow up if you are anything like the other people that I've tried to explain this to. And that's not a knock on you. That's a knock on the fact that we are in advanced multi-level models, folks. Shit gets real here. If this was things that you could teach yourself in 10 minutes, it would not be worth your time, right? So let me put it to you this way. What if I have my level 1 X and my level 2 X, and we're using grand mean centering, right? Grand MC. And then I have my level 1 x times the moderator. That's what I have right now. Put this over here, actually. So I'm missing this cell that's highlighted. In the same way that if you put in level 1x all by itself, you're assuming the between and within main effects are the same. When you put in level 1x by moderator all by itself without the level 2 analog to the interaction, you're assuming the moderation effects are the same between as within. The fix to it is fairly straightforward. We do the same thing at level 2. Makes sense, right? Now this is how within, I can't shape, how W changes by M, we'll call it that. And now you really want to type B here, right? But not under this specification. This is how the contextual effect changes by M. And if you sum the how W plus how contextual, you get the how between. And Excel's like, what? Here, so. How W plus how contextual equals how between. There, got it. Cool, right? With me? That seems not so bad. Now, what if I told you that M equals level 2x? Because that's what we're doing here. So if M, my moderator, is level 2x, or up to this point, where I added the cross-level interaction between the two, this is the cell that we're missing. So what the missing effect that unsmushes my interaction becomes is a quadratic term. Now, both the within lunch effect and the between lunch effect can vary by school composition. You ready to see it? What's the rule with quadratics, folks? Twice the quadratic is how the linear term changes per unit. So we're going to put that same rule to work in the next model. There it is, Model 6, the end of the story. So I have added gamma O2. This is school level lunch multiplied by itself. So it is a purely level 2 interaction, which is why it goes on the intercept line. And because it goes on the intercept line, which variance component should it reduce? Random intercept, yes. Should any of the other variance components change? Nope. We are unsmushing the effect. It will show up in the random intercept as needed. So do you remember at the beginning of the story when I told you I was only going to have one predictor in the story? This is how free and reduced lunch predicts math. How many fixed effects are in my model at this point? Count the gammas. 5. How many parameters in my model for the variance? We'll start at level 2. How many random effects do I have? 2. I have an intercept and a free lunch slope, and I have a covariance between them. Am I missing anything? How about level 1? E variance also. So 4 terms in my model for the variance, 5 terms in my model for the means, 9 terms total out of 1 predictor variable. Survey says, so what used to be an interaction term with a value of 4 was assuming that the moderation was the same between as within. By unsmushing that interaction term, by adding the level 2 quadratic analog here, the within level moderation went to 5, and the between level moderation went to -14. So this is actually contextual right here. The full between is if we were to add the 2 together. Right here, -8. So can I have this p-value be significant so I can talk about it? You feeling generous today? So yes, the extent of the gap between the haves and have-nots at the student level is moderated by school proportion free lunch, almost significantly. The effect of school-level free lunch is not moderated by itself. It's this one right here. That -8 is not significant. So there is no between-level moderation, but there is within-level moderation. So this is an instance in which we would have come to the wrong conclusion, potentially, if we had left the smushed interaction term in the model, because that was biased by the between effect being near 0. So Andrew, you asked me a question like last week maybe, like when conditionality. So this is an instance in which if I were talking about what effect is conditional on what, the effect of school mean free lunch is conditional at 30% free lunch students because it interacts with itself. It is also conditional on a student who pays for lunch because it interacts with student-level free lunch. So it only is conditional on its own centering value if it interacts with itself, which is what it does here. And at this point, you might be looking at this and going, how in the hell would I ever explain this to somebody, right? Anybody thinking that? Wave 'em proud. Yes. You know how? Pictures. So we got another 4% of the intercept variance after fixing unsmushing the model. Here's some words. And here's my picture. I made this picture in Stata. Doesn't it look nice? I also have one in Excel in the Excel worksheet available for download. But here what I have is the x-axis is the student level effect, where we have no free lunch on the left and yes free lunch on the right. Therefore, the slopes are negative. Getting free lunch is bad for you. The lines themselves are for different kinds of schools. So typically, when you're trying to make predicted trajectories or predicted slopes, you might go plus or minus 1 standard deviation. Instead, I chose to go with values that I thought would be more meaningful. So 30% free lunch kids was near the mean of the data. I went 10%, 30%, 50%, and 70%. Those were arbitrary choices, but I know that in the actual data it ranges from 0 to 80, so I wanted to show like what that would look like across the span of the data that we have. So the slope of the line then indicates the level 1 effect. Free lunch is bad for the students. It is less bad if you go to a school that has more poor kids. That's the idea that we have this -8 coefficient that becomes less negative as the proportion of free lunch kids at your school increases. So for instance, if you look at the top line, that's 10% poor kids. The orange line is 70% poor kids. The orange line is less steep. So that's the P equals 0.0522 moderation of the within school effect by school level free lunch. The difference between the lines vertically then, that's the between school effect. The idea that these lines are non-parallel is guaranteed by the between school effect, the contextual, by the level 1. And the fact that these lines are not equal interval, right? There's a bigger gap between 50 and 70 than for the others. That's the quadratic term in the model. The direction of the quadratic term, even though it's non-significant, indicates an accelerating negative curve. It's more and more bad for you the further up you go on that variable. The contextual effect, then, that is directly provided by the level 2 model, you can think of as being the vertical distance for the no kids. After controlling for individual student free lunch status, what is the extra effect of going to a poor school? The differences between those dots give you the contextual effect. So is it bad to be in a poor school? Yes. Is it more bad to be a poor kid? Yes. Is it as much more bad as you would think? No. It's an under-additive interaction. It's less more bad. How's that? Ta-da. So, moral of the story, whenever you are examining interaction terms in these models, think about the levels of analysis too. Anything that interacts with the level 1 variable should also interact with its level 2 counterpart. So if I had a model that had level 1 X, level 1 W, level 2 X, and level 2 W, how many interaction terms are possible there? Well, let's say that I have the main effect of level 1 X here, the main effect of level 1 W, the interaction of the 2, 1 W, Let's start there. What term in the model do those three things, what term are they going to account for? What kind of variance? Residual, level 1. Because these are level 1 main effects, and this is a purely level 1 interaction. Likewise, level 2x, level 2w, level 2x by level 2w. What term in the model are those three things going to account for? It's not residual. What else is there? Something level 2, right? So I have a level 2 main effect, a level 2 main effect, and a purely level 2 interaction. Which variance component does that have to be? Give me an I. Intercept, yeah. So then we get the crazy ones, right? Level 2x times, level 1x, times level 2w. Which variance component is that going to be accounting for? There's two possibilities. Either if level 1x has a random effect, it'll be that one. Or if it doesn't, residual. Yeah, level 1 residual. If I'm using grand mean centering for this level 1x, then I'm assuming that this level 2w moderates the level 1x the same as level 2x. So to unsmush it, I would need to do this, level 2x by level 2w. That would allow level 2w to moderate the within and between effects differently. And then the same thing would be true for the reverse pairing. All possible combinations there. So Chapter 8 in the book has a walkthrough of all the possible combinations if you've done group mean centering for one and grand mean centering for the other, or both the same, or vice versa. That's why it's so long. So it can be convenient to set up all of your level 1 predictors in the same way so that everything is either between or contextual at level 2. But that may not make sense in every situation. Okay, questions? All right, let's change gears then a little bit. I'm not going to go through the algebra, don't worry. It's just there for your reference. It's in the book. More complex designs. So crossed models. How many of you had a really good teacher at some point before you got to college? Hopefully everybody can think of at least one person, right? Do you think that person set you on a better path than you would have been otherwise? Hopefully, right? So, for instance, in this example, we controlled for which school a child was in currently. What about all the schools they would have been in before that? Think that matters? Sure. So if you have that kind of information, that could be something else to account for in your model. But if students don't all have the same matriculation profile, if you have elementary schools and you have high schools, but not everybody who went to the same who goes to the same high school went to the same elementary school, then they're not nested. They're crossed. So it's the exact same idea as the subjects and items. You can have a kid who is nested within their current school, and that same kid is also nested within their elementary school. Just like we did in homework 4 and in the cross subjects and items example, we can do that with 2 random statements. It's pretty straightforward to do, actually. In SAS, other programs make it a lot harder. These are the models, by the way, the cross models that Stata throws up on big time. I had big issues with that with the book. But I can show you what it looks like in SAS with a fake data example that I borrowed from the UPOPS book. So let's take a look at that. Let me check and see if my microphone is still working. It appears to still be working. Hooray! So let's do cross schools. Let's do that one. So he calls them secondary schools and primary schools. I think of them as elementary and high school. This is a simulated data set, I'm quite certain, because there are exactly 1,000 kids, 30 schools of one type and 50 schools of another. Oh, and his SES variable is a continuous variable on a scale of 0 to 10. So, pretty sure this is fake data, but that's okay. So I downloaded this data from the book's website so that I could build an example with this. So the first thing that I did actually is compute school level means for the primary schools and the secondary schools for our student level predictor, which is this SES variable. I then centered at 4, which was near the mean of the variable. So, excuse me, it's 1 to 6. So pupil SCS is this variable he calls PUPSES, which ranges from 1 to 6 with a mean of 4. We also have whether or not the primary school and the secondary school are what he calls denominational. I'm going to go with private. Can we call it that? Does that work? So let's start with the analog of a single-level empty-empty model, super empty E-only model, where there are no piles other than just E. So I'm on the first page here, second page, yeah, first page of example 6b. Here's my equation. Note that I'm picking subscripts that mean something. You are allowed to do this. It does not have to be IJK or any of that craziness. I have kid, primary, and secondary as my letters here. So Y for each secondary school. Actually, no, I take that back. This model has a random intercept. We're not starting with E only because he didn't in his book. We're starting with a random intercept for where they currently are, their secondary school. And this is a measure of achievement. So I have P school and S school as my two level 2 nesting variables, and pupil would be a level 1 variable. At this point, it says that I have 30 secondary schools with up to 48 students per school. I get my two variance components. So UN11 is row 1, column 1 of the G matrix for secondary schools. That's my random intercept variance of 0.07. My residual variance is 0.68. So 0.07 over 0.68 plus 0.07, that would be my intra-class correlation. I am then adding the effect of where you were. Another separate random intercept variance for primary schools. So this allows an additional correlation between children who went to the same primary school, and there's a correlation between children who went to the same secondary school. So a child who was with a peer in both places the same would have both sources of correlation in their data. Now note what SAS does here. You may see this sometimes. It thinks it has one subject with 1,000 observations. Clearly that is not right. What it's actually referring to is the number of observations that have the same V matrix. And in this case, everybody has a different one. So you can just ignore that part. Now, let's see. Not Alexander, damn it, Andrew. Yes, I know. It's like I get it wrong the first time and it sticks. But so here's just a new wrinkle for you, right? 2 UN11s. One for S school and one for P school. So you have to pay attention to which is which and what the order is within a line to know what those things mean. Those are both random intercept variances. So the variance due to primary school is 0.17. Excuse me, that's the variance component. The variance for secondary school is 0.07. And then here's the residual. So we can test whether or not each of these variance components is different than 0 with -2 log likelihood, same as usual. Given that all three variances are orthogonal, I can add them together. So rather than doing intra-class correlation that's between versus within, for these cross models, that starts to become unwieldy and unhelpful. These are just straight proportions. So they're not intra-class correlations, they're just proportions. So about 9% of the variance is because of the secondary school you went to, is due to mean differences in secondary school. 23% of the variance is to differences between primary schools. And the rest, most of it, 68%, are differences that remain between children. It has nothing to do with these schools. So I then added his two school-level pieces of information, denominal status, where 0 is not denominal and 1 is denominal. Private, we'll call it that. They are non-significant and, curiously, the exact same magnitude. Fake data, folks. These are the telltale signs. Just like all of my outcomes are scaled from 0 to 100, no matter what the story is. Yeah. But that's okay. So relative to the previous model, which of my 3 variance components do you think primary private school status would have explained? Primary. How about secondary school status? Which of the 3 would it explain? Secondary. So the rules are the same, even when you get more piles for more reasons. Predictors of that kind explain variance of that kind. If it's a main effect, it's intercept variance. If it's a level 1 main effect, it's residual variance. So the next thing he did in the book was add this effect of pupil SES, centered at 4. And that should have reduced which term? Residual, yeah. So this is, I believe, it looks like smarter kids do, or no, richer kids are smarter or something. I'm not even going to try to interpret that coefficient because I have no idea what these variables are. However, is this the end? Can I just stick in a kid-level variable at level 1 and be done? Nope. Now this is a double smush. Much like double stuffed Oreos, but not nearly as tasty. To the extent that there are differences between primary schools and their school composition, and differences between secondary schools and their school composition, it's double smushed. Because there's 2 kinds of between here, any kind of group mean centering is going to be challenging to interpret. So I left pupil level 1 using grand mean centering, and then I'm going to add the contextual effects at level 2 to see whether or not I can smush this. So I added both at the same time because they should be orthogonal to each other. Here is primary school mean SES and secondary school mean SES. So unsmushing both of the level 2 effects, those will be contextual effects. And lo and behold, they're not significant. So it looks like he generated these data to not have any contextual effects. So there is no extra increment of the primary school mean SES on primary school scores. There is no extra increment of secondary school mean SES on secondary school scores. But those are fixed effects. We can also look at random effects. Random effect of a level 1 thing. So far we've been saying level 1 predictors can have random variation over level 2, right? Still true, however, we have two kinds of level 2 here. So it can actually be random over both, or either, or neither. The advantage for being rich could vary over primary schools. The advantage for being rich could vary over secondary schools. I tested secondary first because what the hey, got to start somewhere. Minus 2 log likelihood difference, 2280 versus 2285. Ooh, that's a close one. That's a nail biter. I left it in and added it to this one. And 2266, that one it does need also. And that was the end of my story. So now each level 2 unit, schools primary, schools secondary, varies in two ways: in average achievement and in the effect of SES on achievement. So to explain the latter, we would need cross-level interactions. We would need student-level SES with primary school predictors to account for this random slope, and we would need student-level SES interacting with secondary school predictors to account for this random slope. The same thing could happen if you have neighborhood data, census data. Students may be nested within neighborhoods. Students may be nested within schools, but not everybody who lives in the same neighborhood goes to the same school. Not everybody who goes to the same school lives in the same neighborhood. They're crossed. So same ideas, just another level of complexity. Order of complexity, not even a level yet. And time's not in the story. So the first time, I think it's the second time, I taught this class as a postdoc at Penn State. I had students who had what they were calling clustered longitudinal data. That's coming later, meaning that it was people followed over time, and the people come from clusters, like schools or classrooms. And I was helping one of the students try to set up an empty model. And I said, okay, so what's your school ID variable, or your classroom ID variable, excuse me? And she said, which one? I said, what do you mean, which one? She's like, well, they were in this class in kindergarten, they were in this class in first grade, they were in that class in second grade. Which one? Shit, you're right. Which one? So I went back through and started reading all the books, and I was like, why doesn't anybody talk about this? Why is everybody assuming that you stay in the same cluster? So that's the example that I have for you next time, is what happens when people change groups over time. Then students and clusters are crossed, not nested, because students move between clusters. So I think that's actually more common than not, but for whatever reason, it's not a model that's gotten a lot of coverage. They go by multiple membership models or cross-classified models. They can be somewhat painful to set up, but I want to show you how to do so, as well as how to think about what are the lingering effects of classroom and what do they mean. So for instance, if you ask a teacher to rate their students on whatever behavior, let's say aggressiveness, how do you know that a student is aggressive versus a particular teacher is just really picky? Well, you'd have to get more than one rating for the student and get more than one set of data for the teacher to rate. Then you might be able to pull these things apart. And the idea of being able to pull apart teacher variation from student variation is the basis of value-added models. So that's what's coming next. But the basic premise then is what happens when people are in groups and those groups change over time. Ta-da! Sound like fun? Sure it does. You're like, uh-huh. The good news, it's just more complicated. It's more stuff at the same time, but there's nothing new. There's nothing new. Level 1 terms can vary over level 2 units. And each level 2 unit can vary over the other. And you have all the skills you need to fit these models. For reals. Any questions before we break for today? All right, office hours start now. Let me know if you run into more issues with your homework, and Lindsay, I will look at whatever's. You got it. What happened? Oh, it just said it detail and it didn't give you anything? Yay, okay. Well, good.